Hello community, welcome to part 2 where we examine how is it possible that a Llama 3 model with an original 8K context length can have an extended context length up to 1 million token or 2 million token. Hey, who cares? Let's do this. And in the part 1 section we looked at rope, we looked at position interpolation, we looked at neural tangent kernels, and we looked at yawn. Now in part 2 of this video, we base our knowledge on this and we extend to have a look at LongRoPE, at theta scaling and at theta scaling with ring attention. Let's start. You remember the core of all is rotary position embedding of 2021. And I told you we just need to understand that the inner product of a formula of our query and our keys, if we do the inner product of them for the self-attention, with the positional information, where is this specific token or word at the position M and here at the position N. We do not want an absolute position encoding, but we want a relative position encoding. If I take this set of equation, and I showed you in the part 1, that there's one mathematical solution, and we have here exactly the solution for our function g. So pure mathematics give us here the correct solution to our problem, and this is not limited to AI. So we have here a complex exponential function that is here with the relative position encoding and our famous theta that we already talked about in part 1. And now we will focus much more on theta in this part 2. So at the end of part 1, I mentioned to you that Microsoft said, hey, now we have LongRoPE, and we go beyond 2 million token if we have the base model of 8K token. So here we go. Just to give you here the information that at this time, we already had the solution for the mathematically correct way of doing 1 million token length. UC Berkeley showed us this in cooperation with Google, what they called ring attention, and I showed you this in this video of mine. They have here a beautiful new parallelization, and they solved this by pure compute power. And I also showed you in this video, we also had here this transformer feedback attention memory solution for 1 million plus token. And we also had at the time the infinity attention for 1 million context length. And no, we did not have it this time because this is a rather new video from me where I show you the next generation AI where we have recurrent LLMs, but also for a long context length with more than 1 million token. So you see, at the time that Microsoft published this, we had the correct mathematical solution that, were based on extreme parallelization of extreme compute power. And Microsoft told us, I would say now that similar to Meta, Microsoft said, do we really have to pay the price of this, that we have to run this system for days and weeks on hundreds of GPUs? Is there a better way, which I would be calling cheating on the mathematics, but maybe? So let's see what Microsoft published, and let's have here an absolute neutral view on this publication by Microsoft. They have 3 findings. They found that the rope dimension that I explained in part 1 of this video exhibits some substantial non-uniformities. So not all are equal, which is not the most effective way handled here for the interpolation. And you might say, yeah, that sounds logic. And they say, hey, we found in our experiment that rope for the initial tokens, at the very beginning of a sentence in the input sequence, they should be extrapolated with less interpolation. So this means, in a simple word, hey, the beginning of the end of a sequence, if we interpolate them with the same power, we get into problems, because this extrapolation fails. So if something is not working, you know what we do? We just skip it. And finding 3, this non-uniform positional interpolation This makes it possible to extend the LLM context window if we do the fine-tuning. And after we did the fine-tuning of the system, and you see, exactly like Meta, we do not want to pre-train the models and pay for the real cost of a good system, but we cheat here and we say, hey, is it possible to just fine-tune it to have it cheaper? And this is Microsoft, yeah? I mean, okay. So this is the 3 findings that they started to work with. And they said, hey, we see, and I showed you in video 1, that these high frequency dimensions are not compressed in the training stage. But low frequencies are always compressed, and the frequencies in the middle are somewhat scaled. And they said, can we optimize this? So they do not change the method of interpolation. They do not change the method of yarn or of anything else. They are just saying, hey, can we take this particular parameter and modify it even so slightly that we get a better performance? And this is the complete idea. You just find better scaling factors, better correction factors for each of the original rotary, position, embedding frequency through and this is now a beautiful word of marketing, an evolutionary search algorithm, like Microsoft called it. I would call it's a simple optimization problem, where you search here for the maximum performance of your system. Let's say we have a 1024-dimensional space, where we have our projection, and then you know from part 1 of this video that rope frequency, we work now with 512 subspaces. In each of those subspaces, we have a 2-dimensional solution to rope. So we have a sparse block diagonal matrix rotation that we apply. And now they simply say, yeah, but is this really the perfect frequency? Let's say 24.8. And they say, maybe we should give this a scalar factor so this frequency from 24.8 moves to, I don't know, I imagine 24.72. So you see, this is now, I can't call it fine-tuning because I need the real fine-tuning later on, but they took now these little screws, the little knobs you have on the system, and they turn it a little bit and they say, hey, can we optimize this a tiny bit and get a better output? And here you have now the complete optimization system. For my green grasshopper, when Microsoft talks about here an evolutionary search algorithm, they have an initialization phase, they have a search space with the rescale factors, they have here what they call a fitness evaluation, then they go to a selection, so they select now at this stage the top performing candidate solution based on their perplexity scores. They go with perplexity as the main indicator to form here the pool for the next generation of optimization. They do some mutation, some crossover. You combine pairs of selected solutions that work and you say, hey, maybe if I shuffle them around, I find a better solution. You have some constraint on the system like, yeah, I formulated it here. Then you iterate again. At the end of this iteration, you have just an optimization problem. And the more compute power you use, you get finally a set of rescale factors and specific starting token. And these rescale factors are now that you apply to the original rope embeddings. So again, if the original rope embedding was, I don't know, 101, and now you have 100.6847. So with these new parameters, you say, what do you do with it? And as I told you, like with Meta, Microsoft also doesn't want here to go with the full cycle in the pre-training. They say, let's fine-tune it, because fine-tuning is so much cheaper. And I would like to say, yes, it is really cheap what you try to do here, but okay, I go with the publication. I'm not emotional on this topic. So after they did this evolutionary search, so they identified now for a particular system. And remember, this is real specific to the system you're doing the optimization on. This is real specific to the domain knowledge that you have in your system. to do the rescale factors on. And if you have a domain knowledge of, I don't know, news in the United States of America, and then you want to apply this to a medical AI system, you might be surprised that the system is not working anymore because those rescale factors were done for a specific domain-specific knowledge. So careful, you have to do this really knowing the limitation of this optimization theory. Okay, and then they said, hey, our method is able, and this is Microsoft, to extend here the Llama 2 context. They did not do this on Llama 3, okay? From 4K, which was the original pre-trained context window. We can do this now to 32K without fine-tuning. We just rescale the factors. You say, So you have an extreme, intense optimization procedure to optimize the original rope embeddings to a slight difference, and okay, you have now new optimized rope factors for each dimension of our 512 subspaces. And you can do this without fine-tuning, but of course, this will be the base for the fine-tuning that has to start sometimes, because what we achieved now is just we go from the original pre-trained 4K to 32K token context length, just by rescaling this, analyzing the system, finding better optimization parameters, and we say, hey, if we would apply them, we could go theoretically to 32. Now, if we have the system where we could apply this to go theoretically to 32, let's start now in the next step, and we go from 32 to 128, and now we really fine-tune the system. And then if we fine-tune the system to a context window of 128,000 tokens, we do another analysis of the parameter, and then we fine-tune it again, but this time to 256,000 token. So let's see this. In the Llama 2, they conducted this search, as I just showed you here, for the target context window size of 128 and then of 256. So you had quite some intense optimization calculation running here on a domain-specific dataset for a domain-specific LLM, given that it was just pre-trained on 8K token length. So, if we have now here, for the target window size here, the correction parameter, you insert this now, you tune your little rope parameters, and you start to fine-tune the complete Llama 2 system with those rope, and I call it rescaled factors. And then they replace here the rope's rescaled factors of the 128 with the, again, optimization problem solved, 256K on the finish checkpoint, and then they start another fine-tuning session. And Microsoft tells us here, hey, we just used here 8 times an 80 gigabyte A100 NVIDIA GPU, and after some time, some days, some weeks, we had a solution. So you see, this is something that is interesting. But we are still at 256K. How do we go, as they claim here, 2 million? And then they say, okay, if we have this, we perform a secondary search, and you know, search, this is here the search, so again, everything. Now on our fine-tuned 256K length LLM. Now remember, this is quite now an extensive, a quite complex LLM. If you do here complete optimization routine, yes, you need here half a terabyte of VRAM or maybe some terabytes of VRAM to do this. But okay, you can do this. So, and Microsoft tells us, hey, this ultimately results in an extreme large context size window of 2 million token without any further fine-tuning. Interestingly, they do not even fine-tune their final results, because now it will get really expensive if you run this now for, let's say, 2 days, maybe. I mean, Microsoft on 8 NVIDIA GPUs, you know, this would cost, I don't know, $50, no? So without further fine-tuning, we take now the result, and we have here 2 million token context length. So what we achieved here is now, from our 4K, we have now an extension ratio of 512 times longer context window. Now you judge if you would trust this system in a medical AI system. In your financial data AI, would you trust this system that it gives you the correct answer? I think this is interesting, but let me focus on something else. Because in this study, they found something that they said, hey, this is great. And I would like to show you that now we know something that even Microsoft at the time, just 3 months ago, could not explain. Look at this. They said here, hey, we just fine-tuned the Llama 2 only for 400 steps. Short period of time. And then again, the fine-tuning only 600 steps. So this was real fast that we got a result that was good enough for us. And they did a lot of performance tests and complexity tests, and you can have all the information in the study. Please read the study to have an independent opinion for yourself. And you might say, hey, if after such short time they received a good result in the fine-tuning, and in this in this video where I said, hey, new tricks for fine-tuning LLM, I showed you this particular information. That if you fine-tune an LLM, and we decide now between known training data in the fine-tuning in respect to the pre-training phase, or unknown training data in the fine-tuning with respect to the pre-training phase, we have a beautiful exponential accuracy that builds up, and then we plateau out at 100%. But if we do this with unknown data, my goodness, where overfitting starts, we are below 20% performance. And remember I told you here, whenever you notice here in your development accuracy data set, that here we start to have the overfitting of the LLM, do an early stop. And you might argue after you have seen my video and you are a subscriber of this channel, hey, is this exactly what's happening here? Is this that just after 400 steps, a very short training period, we already reach at maximum performance of the system because this is the benefit of the early stopping? Well, it's a good guess, but if you remember this video just 2 weeks ago where I told you we have a new discovery and Microsoft did not know about this. I have to tell you, this was unknown when Microsoft published this. And I told you we, the community, discovered here retrieval heads in our LLMs when we do here AI agents. And you remember this particular piece of information that I showed you. If you have a Claude 3 200K or a Gemini 1.5 Pro 1 million, the old version, if they look here at the particular heads in our LLMs, and we analyze what is each particular head in each layer doing for us, we have specific for the long context transformers. We discovered that there are special long context retrieval heads. And unfortunately, they are less than 5% of all the attention heads. And we calculated here a parameter, and I showed you, depending on the system, a Llama 2 or a Yi or a Q1 or a Mixtral, sometimes we only have 0.7%. Or maybe 0.5, and then maybe if you take here the 3, so this together here, the red and the orange, it is below 5% of all the attention heads that are available are actually doing the job for a long context retrieval. So this happens on very selected heads in our LLM. And this varies across the architecture from a Llama to a Yi to a Mixtral. So you have to analyze this. But if you can identify those heads and you hit those heads with your fine-tuning, then the miracle happens. And what Microsoft could not explain at the time, end of February 2024, now you understand this. Because We discovered in the meantime the retrieval heads in our large language model, and now we understand if you hit these heads and you train it just a little bit, since they are doing all the job for the long context retrieval, this is all there is. I don't need all the other 95% of the heads in our LLM to do their job, because this is not the job that they're doing. So beautiful. But wait a second. We are not done now by the methodology of Microsoft research. But I think it's interesting if you have the latest research results and you look back here at a publication that is just 2-3 months old, and there was something nobody could explain, not the thousands of researchers at Microsoft, that now we can explain it. And I think this is the beauty of AI sometimes. But yeah, at the original paper of Microsoft Research, they noticed something. After they have done all of this, so they went from 8K to 32K, then to 128K, then 256K with the fine-tuning. And then they analyzed the corrective parameters to the row parameters, and they went from 256K without fine-tuning, which is a mistake, but never mind, to 2 million token context length. They noticed something. And they said, hey, if we look now at this optimized system where we run optimization for weeks, there's a tiny little problem. That the original LLM that was pre-trained on 8K token, it completely is unusable. So now in the words of Microsoft, after achieving the extreme long context length window, 2 million token, this search is now adjusted to recover the performance in our context window of 4K and 8K. So what they tell us here in this sentence, that after all their performance and their extension and their interpolation and their yarn optimization and their complete system optimization, after all this optimization, their main workhorse where people use an LLM to 90% of the time within the 8K token window, that this LLM was not working anymore. And after all the optimization to 2 million, they look back at the 0 to 8K token window, and the LLM could not perform the task anymore because the base from which all started has been so heavily modified that the base fails to perform as an LLM. So what they do, they had to adjust the complete 8K token system to recover the performance, to rebuild the base. Imagine you build a house and you start with the base. It's cement. And then you start with the first floor, then you build the second floor, and then you fine-tune the third floor, and then you say, I know I go from the third floor to the fourth floor without fine-tuning. And after all those modifications, I notice that the base of the house is not working anymore. So now after I build the house, I just have to swap out the base and build a new base. I don't know if this is the perfect way to build an optimum performance system for a medical AI system or a financial AI system. But I think it shows us some interesting way if you end up at the end of the optimization that the base system is not even performing anymore. Hey, you just correct the base system. I mean, you have corrected everything else in the system. So yeah, this is what I feel about this particular publication by Microsoft Research. Now, if you have an eagle eye, you noticed that I skipped over half a sentence. And this half a sentence is, let's go back. I'll show you. Where is it? When we did here this rescaling of a 128K context length, I would have liked that doing this analysis, we use also a training data set that has also a 128K sequence length as our training data. Because deep inside of me, I believe if you optimize a system for a sequence length of 128K, you should have training data that extend 128K. However, to build an even cheaper model, there's now the solution that you do not use a 128K long sequence training dataset, but you stay with the original real short training dataset. Let's look at this. Okay, again, we start with the pre-trained model, and for Meta or Microsoft, normally 4K token or 8K token. Then we say, hey, we know RoPE for this beautiful rotary position encoding. So we use RoPE here, which is mathematically perfect for positional encoding that is only depending here on the relative position of the distance of the specific tokens to calculate here the self-attention, not just by adding here an absolute position embedding, but adding a relative position embedding, and we do not add it, but we have a more complex operation. So this means that each token position is encoded using now the rotary matrix I showed you in part 1 of this video. And now Microsoft says, hey, and now we have our LongRoPE search optimization. And okay, this is an optimization methodology, accepted. And then, as I told you, we have the original RoPE embedding. Really the data here. Those were designed for a shorter context window, 4K or 8K. And this is now modified using now the searched rescale factor that I've shown you, the optimization topic. And this effect is essentially projecting the original RoPE encoding onto a much larger range of position. You might say, yeah, this is of course the extrapolation that we have. Now, Microsoft would like to note that this is not an extrapolation, but this is called a projection of the embeddings to a larger range of positions. Okay, I can accept this, another wording, but we know what it is. And then when we fine-tune this with our modified RoPE, beautiful. The model is then fine-tuned, correct, with this modified RoPE parameter, yes, correct. But using the same dataset that it was originally trained on. And this dataset contains shorter sequences. Now, if you do a fine-tuning on a system that was 4K or 8K token in the original sense, and you do the optimization problem, and you do the RoPE calculation and the correction factors to the RoPE embedding, and then you do the fine-tuning, and after you do done all the optimization, but then you say for the dataset for the fine-tuning, I use the original dataset. I might ask you, do you think after all of this, and you go to 256,000 token context length, that for the fine-tuning process, it is adequate to use the original dataset, the real original dataset it was pre-trained on? I personally think we could optimize this if we would use here in the fine-tuning process also a fine-tuning dataset that has, if we do for 128K, also at 128K context length. But I know this would increase the cost for the model. I get it, yes. But doing all of this optimization and then in the final fine-tuning, when you say, okay, now we have other parameters, so we re-fine-tune this. Then you go with the original short sequence dataset. I might have some ideas about this. Yeah, what is the key takeaway? As I told you, please note, I want to stress this is not a dataset extension, but this is just a projection, okay? And they state, yeah, it's true that the fine-tuning process is crucial to adapting now the model to the new RoPE embedding with the correction factor. But when they say, despite using the same shorter training data, I personally would like to see a further improvement in the system performance and not go with the short training data, although I understand it makes it cheaper for the company, for Microsoft, to invest less in the research. I get it. It's optimization problems, how you maximize your profit. And then they proudly state that this strategy minimizes the need for extensive dataset changes, making LongRoPE a more practical and efficient method for extending context windows in LLMs. Okay, this is, the statement. And now I wanted to go there. And they say, hey, we have the code open source, it is on GitHub. And I go to GitHub, I go to Microsoft exactly to where it is, and I don't find it. So I go to Microsoft and I look in the repositories and LongRoPE, exactly like they published in their official archive, in their preprint. And I go to LongRoPE, and today I see they deleted everything about it. And then we have this beautiful publication from Shanghai AI Lab and Fudan University, mid of March 2024, about the scaling laws of rope-based extrapolation. Please note, not interpolation, extrapolation. And this is now important because you remember when I showed you in the first part of this video that we talked here about rope and the higher dimension, that we have a sparse block diagonal matrix here, where each block is a two-dimensional rotation matrix. You remember that we had here in this rotation matrix here our theta 1, theta 2, theta 512. And I told you this theta I is here identical to the original theta that was chosen by Google in the All You Need Is Attention paper with a base of 10K, 10,000. Now this is important because this team of researchers found out that fine-tuning rope with either a larger or a smaller base than 10,000, using now the original pre-training context, can boost the length extrapolation of our rope-based LLMs. And this is a beautiful visualization. Look, in the middle we have our rope base of 10K. This is the original Google publication from 2017. And you see here the periods of the cosine with theta n, and we have a 4K training context length. And let's have a look at this. And we compare this system performance here with a rope base of 500 and a rope base of 1 million. And we say, what changes in the system? What does it affect here? Now we can say for rope tuned with a base 500, all the periods of a cosine theta n are limited within the 4K training context. With our 10K, and we do not know if 10K is really the perfect rope base. We have to find this, we have to verify this. But at 10K, the periods of the dimension past the critical dimension here in red stretch beyond the training context. And at 1 million plus the base, not the token, careful, only the dimension past the critical dimension fail to extrapolate. And you said, okay, what is the critical dimension here? And the base 10K causes periods of certain dimension to extend beyond the training context of 4K. And therefore, there exists a specific feature dimension that we call d extra. Now, this is important. In d extra, what is it? Is it exactly in the mathematical sense? It is the number of dimensions where our orthogonal system of the cosine and the sinus can cycle through their values within one period, either pre-training or fine-tuning, a complete one cycle. So this means that the dimensions that go beyond our d extra, when rope-based LLM extrapolate beyond the training data, this absolute position information of newly added tokens and the relative position information in relation to the previous token, they become OD, out of distribution. So we have a misalignment suddenly beyond a certain threshold. This means that the attention scores related to those dimensions deviate from their expected distribution, causing here our OOD in the overlay attention scores, and we get a problem. And this problem is called the extrapolation issues. And we refer to this key dimension, d extra here, as the critical dimension for the rope-based extrapolation, and the authors defined here the d extra as the critical dimension in this particular way, so we can calculate it for our systems. Now this is interesting because if we look now at the critical dimension for extrapolation, and we see in our system we do have it, so we have in blue here a reliable part for doing our extrapolation of a periodic cycle, and then we have a part that OODs. And this is exactly here. It starts with d extra and goes up. So careful. This works. Here we get problems. And now let me show you here the data of the study, and I think this is beautiful. So what they did, they had a Llama 2. This is what was known by heart, with 7B free trainable tokens, and the original training length of 4K. Yeah, let's do this first. And you see here the original rope. This is here. This goes here. So, my goodness, yeah. This is here the context length of 20K. So at 4K, this is here the limit of 4K of the pre-training. If we then had now the rope with a base of 1 million, with a fine-tuning of a 4K context length, you see suddenly we're here in this dash dot dash blue, we're in this line. And if we look here at the y-axis of the perplexity, you see the perplexity stays really low. This is beautiful. This is what we want. But you also see that the best performance is this solid blue line. So this means if we calculate rope, not with a base of 10K, with a base of 1 million, and we do the fine-tuning with 16K context length, we get a performance for a Llama 2 7B free trainable parameter that is, wow. You see here the perplexity stays constant low up to 100,000 tokens. So this means if we change here the base of our theta for the positional encoding in rope, for a Llama 2 7B, yes, there seems to be a possibility to go really up to a context length of 100K. And this is amazing that they did here all these experiments, and you see here all the other data. Now, you see here also that there's a rope, base 500 in solid red, with a context length of 16K, that is also not bad. Look here, this red line is also going to 100,000 token context length on a Llama 2. So you might say, this is now interesting. So I have a 500 and a 1 million, and both systems are performing if we have this base. And they tested it here for a short context length with this particular benchmarks, and they tested it for a long context length with this particular benchmarks, and they found, yeah, look at this. This is now rope fine-tuned, the result, with a 16K context length. Not 4, not 8, 16K is the crucial importance for a Llama 2 7B. And what you see now, this is the classical 10K. This is our base from the attention that we had. But if we now check here with different bases in our theta, you see that the 500 performs really well, and the 1 million performs really well if we have just one benchmark, that is perplexity. So if you ask me, is 10K as the base in our theta definition the best base for a Llama 2, I have to tell you no, because we have a 500 and a 1 million that is significantly better. We have other bases, like here 20,000 or 40,000 or 80,000, that is significantly worse than our 10K. But they are those two that are significantly better. And now we have kind of a problem, no? Because you would expect, hey, either more or less, but both? How is this possible? So if 500 are in green, so we say smaller bases, so 500 is smaller than 10K, also promise a better extrapolation of our LLMs. However, while the improvement is not so uniform like in something else, the resulting extrapolation curve does not have an obvious breaking point, a limitation where it says, until this point and no further. Does not have an obvious breaking point. This is interesting. But also we have our 1 million. So we have a larger base. This also promises you a better extrapolation. Look, 100,000 token, 100K. However, this has a clear limit, and beyond this limit, the extrapolation performance declines significantly. So we have now two cases. The smaller base has not a uniform improvement, so we have to find the sweet spot exactly, these local areas where we have a boost in the performance, but there's no obvious breaking point. Or we go with a larger base that has a limit, but it's much more smoother below this limit, below this threshold. So they say, okay, we have to look at both cases. So let's go first with the smaller bases. They also promise a better extrapolation than our 10K base. So here we have our beta. The base is now smaller than the classical 10K base from Google at the very beginning, 2017. So what they say, for rope-based LLMs pre-trained with a context length T-train, 4K, 6K, 16K, if we adjust the base of theta to a beta that is now below 10K and conduct fine-tuning still with the context length T-train, the extrapolation performance, careful, we're talking about the extrapolation performance of those rope-based LLMs will improve. We just have seen it. And if we have here a particular, you remember we have the cosine and the sinus, if we have particular points, we have 3 points of half pi, pi, and 2 pi, then we have stable island of improvement. And for the Llama 2, we can calculate here with the context length here of 4K. We have these particular points at 2.6K, 1.3K, and 650. So this is real close to our 500 that we found just testing. So it is worth noting that these 3 bases align with the pivotal points where the improvement speeds up. So this theorem 1 tells the improving paradigm of base reduction. We go to 500, but we have an improvement in the performance at this 3 parameter. Really interesting. And now, unfortunately, now we have this because we have a periodicity in the system. They say now, since it does not set an explicit extrapolation upper bound and upper limit, rope with a much smaller base like 652 or 500 can potentially, theoretically, realize an extrapolation to infinity. And this is something that, infinity. We have 100,000 token context length, and then to say, yeah, it can go to infinity in theory, yes, but I think to really build system with 1 million, 5 million, 10 million token context length, it is not that trivial. Let's look at the second theorem. Now remember, we had also the larger bases. So more than 10K in our theta definition gives also a better extrapolation behavior of our rope-based LLMs. So if we adjust the base now significantly more than 10K and conduct the fine-tuning, still with the context length from the original one, the extrapolation performance of the rope-based LLM will improve. The extrapolation upper bound, remember we have an upper bound, is calculated as follows. Inversely, if there is an expected extrapolation upper bound, then the smallest capable base, beta 0, is calculated in this way. So you see, we have now suddenly a critical base, beta 0, for the extrapolation. And we will look at this in detail in the next theorem. But however, before we have to say, okay, we have now a theory. This is in red. And then in blue, we have here the practical experiments that we do and how well does it fit. It is not perfect, but come on, this looks really nice. So we have here the max context length and we have here the rotary base values here. And you see for 10K, we have here the larger basis. So beta bigger than 10K. We start with 10K and we go here to 800,000 as a base value. And here we have the max contact length from 20K, 40K, 60K, 80K, 100K, 100,000 token. And you see we have a beautiful validation of our theory by our real-world example of Llama 2 7B. Now, an interesting point is, what about a Mistral? What about a Gemini? What about other architecture? Are those the same theorems? I am not sure that we can go with those theorems for other architecture because this is a really Llama-specific study. But maybe if we further investigate, we will find, if you do your PhD in computer science and you have an AI topic, why not take this topic for your PhD thesis? And in the annex, you find the theorem 3, and this combines now our two theorems, and it is called now the extended scaling law of rope-based extrapolation, with a little bit more detail of the parameters, but this would be too much of a deep dive. Have a look at the studies. I really recommend that you read it. What you take away, and let's focus here on Llama 2, this critical dimension you can calculate, and for Llama 2 it is 92. Now this implies if we have here for the heads in Llama 2 a dimension of 128, this implies that only the first 92 dimensions, where we have the query and the key vectors of our Llama 2, have seen the complete positional information during the pre-training phase and therefore are trained perfectly. In other words, this means the rest of the 128 minus 92, the 36 dimensions, lack sufficient training. So this is interesting. So this means now, if you design now your LLM from the clear extension of our rope, we have now boundary conditions that reflect back on the optimal dimension in the architecture of the LLM. And for Llama 2, since the periods of the first 92 dimensions fit within the training length, these feature dimensions start with a strong foundation for fine-tuning, adjusting to the new period shift of positional embedding for extending cards. So everything is fine in the first 92 dimension, and this is great. But we have to also to take care about the non-so-well-performing 36 dimension. However, coming to an end here with this study, I think fine-tuning, they also stress here, is an essential part of this process that enables this theta extrapolation, or they call it also theta scaling, to be really effective in an extrapolation for more context length. And by adjusting here the rope base value of theta and fine-tune the models with these new values of this base, these LLMs can learn to generalize better to longer sequences when they perform here the theta extrapolation. And this fine-tuning process ensures that the model adapts to the new periodic information introduced by the new theta-adjusted base values, thereby improving its extrapolation capabilities and extending its effective context length. So you see, this is a very interesting study showing us here two segments, a 500 and a 1 million base, and clearly indicates we do not understand in depth what is going on in this system. We just found that 10K is not the perfect way. We have identified our sweet spots. We have identified that they are absolute limits. But to really understand the system, we are missing some research, particularly on this topic. At the end, I would like to give you now a personal outlook. I found this repo here because I also tried to give my models here a larger context window. And since Microsoft deleted here its solution that it published officially, I found here from Singapore, the Technical University, this easy context that is called. And thank you for publishing this solution. And they also focus here on memory optimization to extrapolate language model context length to 1 million token with minimal hardware. And they give you the complete code. And give you also an example here. If you go for a Llama 2, 7 billion free trainable parameter model, if you go here to a 700,000 token context length, you need 8 A100 NVIDIA GPUs. And if you want to go here on a Llama 2 13B model to 1 million token length, you need 16 of these beautiful A100 NVIDIA GPUs. So they tell you, hey, listen, this is not an easy fine-tuning task. No, this takes compute resources, where I would like to understand, hey, how far are we away from the beautiful ring attention from UC Berkeley, that is a real solution, with these approximations. I can give you an answer right now, but maybe in a later video. What I like in this particular GitHub repo is, oh, great, yeah. So at the very last line, you see no approximation used. The models can be trained with full fine-tuning and full data set. And this is what I like. Yes, it takes time, but you got a model with 1 million context length. So you have kind of invest one time. Yeah, and they tell you, hey, we support different sequence parallel methods. Of course, ring attention, the dominant one. And a particular implementation that I will have to look into in the next weeks. Then distant flash attention and some other implementation I will have a look at. I can't tell you yet, but I think it's interesting. And they also say, hey, we try now to have here the rope base frequency to 1 billion. This will be interesting. So you see, currently a lot of research going on in this particular topic, and they give you here the complete code. And the second example I personally will look in is here Gradient, a startup, AI startup here. They just got, I think, some funding, $10 million. And they have May 17, 2024, also some nice ideas. And they apply this. They also rent out here cloud compute space here for you if you need 8 times an H100. But they also do here this scaling rotational embeddings for long context language model. Really interesting. And they say, hey, we managed to scale the context length to 4 million token. And now on a Llama 3 with a full context length supervised fine-tuning. And they go here with the LongRoPE Theta scaling that I just showed you. And they have the compute infrastructure. Yes, you have $10 million. Me too, I would like to have this amount of money. And they do it. And this is great. And I will have a deeper look into this company. Maybe you also want to have a look at this. But you know what I found interesting? Achieving now this outstanding 4 million context token length. It is not important that you can build it, but it has to have the performance if you do causal reasoning. And I was a little bit skeptic that this extrapolation and interpolation and squeezing, and even if you have correction factors to the rope embeddings, there is a natural limit where it simply will stop to work. And interestingly, and I had to smile, they say, hey, we achieved this world record of 4 million context length for a Llama 3, 8 billion instruct LLM. By combining here the theta scaling laws that I just showed you with the ring attention. And I said, okay, now I understand where our journey is going to. You have to rely on this massive parallel, real compute intense ring attention to have a good solution, to be really able to apply maybe causal reasoning to 4 million context length. You can't cheat your way into this regime. But maybe you can apply here some crucial details of theta scaling to have kind of a cost optimization. I'm open to this. But the base has to be solid. So this is just what I discovered just minutes ago. I can't tell you how good they are, but I think it would be interesting to have a look at them If you know them, if you've experienced them, please leave the community here a short comment here in the description of this video. I think it would be really interesting to find those high innovative AI startups. And they try here just 2 days ago these new approaches. They combine this theta scaling with ring attention. And I think this sounds like an interesting way to go to really have the Llama 3 at B with a 4 million context length and then do causal reasoning. And then the question is Llama 3 8B good enough from their architecture to have a 4 million context length? Or is this not the way to go? I hope you enjoyed it. You had some fun with this 2-part video complex here. But there was so much information I wanted to give you, to provide you, to understand here the basis and to understand here the last development of the last 2-3 years it happened. They are not that trivial, but if you look at them in total, you see really here a beautiful path through this theoretical approaches to the optimization, where some companies wanted to go and not invest the amount of money needed for the real pre-training or maybe for the fine-tuning with the real complementary context length. So there you have it. This was the part 2 of my video where I showed you, you asked me, hey, we see now these Llama models here. They do not have the original 8K context length, but they go here 250, 1 million, 2 million, 4 million context length. How they do it? Is it theoretically possible to do it? What are the mechanisms that we have today? And please, again, I want to focus here on rope, interpolation, kernel, yarn, LongRoPE, the theta scaling, and the theta scaling with ring attention. This is intensive. This is compute intensive. I know there are also some people saying, hey, can you show us how to do this here on RTX, I don't know, 3090 for my gaming PC at home? I have to tell you, at the moment, we are so much focused to understand here the mechanism that we can apply, I would say, parallel to the powerful ring attention, where we have a massive parallelization on our GPUs and our TPUs, that for the moment, if you say on a consumer GPU, there's almost no chance that you can do this. I showed you with theta scaling. They were operating here. I think their minimal cluster were 32 A180 gigabyte GPUs. So you see the GPU node that we need here for the scaling operation are quite massive because, hey, our job was to go from an 8K pre-trained context length to, let's say, 2 million context length, which is an amazing work to do. And therefore, I know that some people would like to have a consumer-graded GPU doing this. But unfortunately, the research is not that advanced yet. We still fight here to find here the perfect methodology. But I think the advancement we do in AI research, they are currently breathtaking, and every week we have some new research. So maybe you're interested, and I see you in my next video.